Hello students, in this video we'll prove the Gauss-Lucas theorem. The Gauss-Lucas theorem is a beautiful theorem in complex analysis. And there are many very nice extensions of this as well, which we'll discuss in further videos. What does the Gauss-Lucas say? It says given a polynomial of degree n, of course these are complex polynomials, right? What do we know about polynomials of degree n? I can write them as some number lambda, z minus z1, z minus zn, right? So in other words, I can factor by the fundamental theorem of algebra, right? So what I've done here is I've just used the fundamental theorem of algebra, right? Okay, so in other words, I write the polynomial as z minus z1, z minus z2, z minus z3, z minus zn times some number lambda, right? The lead coefficients, okay? Easy enough, right? We're very comfortable with that idea. And so now the question becomes is we're going to let zeta 1 through zeta n minus 1 be the roots of p prime of z, okay? Then Gauss-Lucas says that then these points, zeta 1, zeta 2, zeta n minus 1, the roots of the derivative, are contained in the convex hull, of the roots of these things, right? The convex hull of z1, z2 through zn. Beautiful. That's a remarkable theorem, actually, right? Now, what's convex hull? Recall, the convex hull, if I give you the convex hull of some points, let's call the points, let's say A1, some complex numbers A1 through AN, for example, what would the convex hull of those things be? It's the set of all linear combinations, the sum, j goes from 1 to n, of tj times aj, such that the tj are real, and tj is between 0 and 1. Okay. There's convex combinations of these things, okay? Now, of course, that's the analytic definition of convex hull. All it means is the following. It means that if I give you some points over here, there's z1, z2, z3, z4, z5, the convex hull just connects all of them with lines. Like that. That's the convex hull of those points, z1, z2, and 3. Gauss-Lucas says what? Gauss-Lucas says, okay, well, the zetas, zeta 1, zeta 2, could be on the boundary, right? Could be on the boundary. So zeta 3, perhaps, zeta 4. They could all be on the boundary. They could all be on the interior, right? That's what the Gauss-Lucas theorem says. Let's prove it. Okay, so I have to somehow come up with this linear combination. So here's the idea. The idea is, let's consider proof. If P of z is lambda z1 zn, then I'm going to do the logarithmic derivative of this thing. Recall, I'll tell you what that means in a second. Then P prime, then P prime of z over P of z, the logarithmic derivative, is going to be the sum of the reciprocals, right? The lambda is going to cancel out. It's going to be the sum. J goes from 1 to n, 1 over z minus zj, like that, okay? So, of course, what's the idea? The idea is that if I want to do a logarithmic derivative, so if I have f1 through fn, take the log of this expression, call this expression over here I, then the log of I is just the sum of the logs, right? Log of what? The log of f1 down to the log of fn. And therefore, if I do the derivative of both sides, so I prime over I is the derivative of I, right? Is going to be what? It's going to be, well, the log of f1 is going to be f1 prime over f, right? All the way down to what? All the way down to fn prime over f, like that, fn. And then what you do is you just multiply by I over here to compute, then what will I do? So I is going to have all of the fn's, right? So all of them are going to cancel out. You can get a common factor, and you'll see exactly that's the expression of it. So that's the idea, that logarithmic derivatives are some like a linear thing, right? So that's the idea behind logarithmic differentiation, okay? All right, excellent. So in other words, I have my p prime over p is what? Is the sum of f prime over f1 prime over f, right? And so of course everything is just going to cancel out. The f1 prime is just going to be what? The f1 prime is just going to be 1, right? Over 1 minus e1. So in other words, this formula gives me exactly this expression over here, okay? That's just logarithmic differentiation. Now the idea behind this is this implies that if I plug in any of these zetas, right? So since p prime of zeta j is equal to 0, that implies what? This implies that the sum j goes from, right, I use a different index now, so let's use a different index. I goes from 1 up to n of 1 over zeta j minus zi is equal to 0, right? Excellent. Okay. Actually, let's do this. Better yet, let's not put an index over there. Let's just actually just treat zeta as any one of those zeros. We don't actually need the index over here. So let's maybe just modify this to make our life a little bit easier, right? This implies that if zeta is equal to zeta j for some j, this implies that the sum j goes from 1 up to n, keep my notation consistent, 1 over zeta minus zj is equal to 0. Okay? I just plug in zeta over here, that's 0. So if I plug in zeta over here, it has to be 0. Good. Now I'm going to take the complex conjugate. I'm going to simplify this by saying that this implies, that the sum j goes from 1 up to n. I'm going to put the multiply top and bottom by zeta bar minus z bar. So in the denominator, I'm going to have a zeta minus zj squared. Now, of course, one thing that might be a problem, right? What happens if zeta was a root, if zeta happened to be a root of z? Then I couldn't use this formula. But if zeta was a root of z, that would just say you're over here, right? You're one of the vertices of this convex hull, and you're still in the convex hull. So that's a trivial case, right? So when zeta is when one of the z1s corresponds to when one of the z's corresponds to one of the zetas, then you're at one of the vertices and you're actually on the convex hull. No problem there. So we can assume that these things are never 0. Then I have zeta bar minus zj bar. Good. Equals 0. And by subtracting, this implies that the sum j goes from 1 to n of zeta over zeta minus zj squared is equal to the sum j goes from 1 up to n of now zj over zeta minus zj squared, right? And now, of course, I can pull the zeta out that isn't dependent on j. And so this implies what? This implies that zeta, and now the formula gets a little bit messy over here, so just bear with me over here. It's going to be the sum j goes from 1 up to n. Then I'm going to have a zj. Let me give myself a little more space over here. Then I'm going to have a 1 over, so like this. I'm going to have a zeta minus zj to the negative 2. That's this thing over here. Divided by what? Divided by the sum. I'm going to change now the I goes from 1 up to n of what? Of zeta minus zi to the negative 2. Okay? Now, of course, this zeta minus zj to the negative 2 is one of these terms down over here, right? So this number over here is a real number. This is a real number, and that's less than 1, right? Times what? Times zj, right? So in other words, what's my combination? My tj here, my tj is going to be zeta minus zj over what? Over the sum I goes from 1 to n of zeta minus zi squared over here, and that's of course a squared, right? Negative 2. Do I have this right? Yeah, negative 2, negative 2. So I need a negative 2 over here and negative 2 over here. Good. Okay? And so these tj's are between 0 and 1. Good. In other words, zeta, one of these roots, is a what? Is a convex combination of these ZJs. In other words, these roots of the polynomial, the roots of the derivative are in the convex hull of the roots of the original polynomial. Awesome, right? Now, of course, the one really cool thing over here, which we're going to discuss in further videos, you might say, can we get anything else out of this, right? And so in particular, if I give you 3 roots over here, so I give you a triangle, there's my nice triangle. Triangles are sort of the easiest thing to handle, right? Z1, Z2, Z3, and let's assume they're all distinct, right? If they're all distinct, then that means there's no repeated roots, and it turns out that what happens over here is that midpoint, 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 there is a unique ellipse. My ellipse is terrible over there. And the foci of that ellipse, and this ellipse is inside, it's inscribed in the triangle, and the foci of this ellipse, and the ellipse transverses the midpoints of the sides of that triangle, and then the foci of that ellipse are the roots of the derivative. That's zeta 1, zeta. We're going to prove this in the next video, right, in a future video, right? And this is called Marden's theorem. Okay? In Marden's theorem, we can prove Marden's theorem. So of course, it's a fancier version of this Gauss-Lucas theorem, right? So we can prove this Marden theorem by appealing to results we have about equilateral triangles. Remember, we have all these videos on equilateral triangles. When is a triangle, when do points in the complex plane form an equilateral triangle? Well, if I had Z1, Z2, and Z3, we said, oh, then Z1 plus zeta Z2 plus zeta squared Z3 have to be 0, where zeta is what? Is one of the third roots of unity, right? That gave us an equivalent, that gave us a criterion for equilateral triangles. If we use that criterion for an equilateral triangle together with an affine map, which is going to preserve triangles in the complex plane, we'll see that this actually follows from some of the earlier results we have about equilateral triangles. So it's all basically starts to fit together very nicely, right? So they get this beautiful result, which we'll talk about in further videos. But nonetheless, many math competition problems involve this idea, this Gauss-Lucas idea, which says that if I give you a polynomial, right? Okay, so the polynomial has roots in the complex plane. If I look at the convex hull of those polynomial points, then the zeros of the derivative of that polynomial have to be in the convex hull. Very useful geometric characterization, because it allows me to say where certain roots are in certain half spaces or half lines, right? So it's a very useful geometric construction. It's very important in the study of convexity. Thank you very much.